Everyone, so today we're going to be going over random forest. So random forest, we can think of random forest as if we have these bunch of these different predictors. We want to divide the predictor space optimally such that we're minimizing the SSE or the sum of squared errors. So as an example, if we have x1, x2, x3, and our target variables, let's say just y, we have these sample data points here. And what we're trying to do with random forest, or first let's explain what decision tree is. So first, decision tree is building these splits, and one of the ways we can do that is through what we call recursive binary splitting. So we're trying to build a tree where we're dividing the predictor space into different segments. And so first we start at the leaf node, then we divide, we find the most optimal split. Again, also this is called the greedy approach because we're finding the next best step or the next most optimal step, which isn't guaranteed to find the global optimal. It's possible that choosing the split that has a slightly higher SSE, but later down the line that might lead to an overall lower SSE. So we're just looking at what's the greatest reduction in SSE that we can get when we're doing these splits. That's why it's known as a greedy approach. So we can think of these as if I have this node over here, and my first step is to figure out where are these splits coming from. So in the case of regression, we have different partitions. There's many different ways to partition this data. And typically we use the midpoint of two consecutive numbers. So in this case, x1 equals 63. That's one partition, so greater than or equal to 63. X2 equals the average of these, the midpoint of these, the midpoint of these, midpoint of these, and so on. The split points or the options for the split points will always be, or not always, but in the case of regression, it would typically be the average of the two consecutive values of that column. And so 63 and so on, you can see that. And after we figure out the splits, the possible splits, so in this case, x1 could be 63, x2 could be 83, x we'll just say split option. So split one, S1, S2, S1, S2, S3, so on, S4. So these are, we find what are all of the possible split options. Then we evaluate the splits. How do we evaluate the splits? Well, we take the sum of squared errors. How can we take the sum of squared errors? Well, if you imagine this predictor space, and let's say we only have two variables, let's say our two variables are X and Y, and we're trying to divide this predictor space such that we achieve the greatest reduction in SSE. So let's say if I divide this predictor space at x equals, let's say w, if x is greater than w, we move on to the right side of the tree. If it's less than w, we move on to the left side of the tree. So how do we know if this is the most optimal split? Well, if this is the most optimal split, we want to see which one minimizes the SSE the most. So we have a bunch of these different splits. We want to see which of these splits is going to minimize or provide us with the least sum of squared errors. And so let's say we have a bunch of data points. So once we do the split, we have a bunch of data points here. We have a bunch of data points over here. Now, how do we find this sum of squared errors? Well, here for this, the prediction will be the average of these values, and the prediction for in this region will be the average of these values. So that's the prediction. Now we can figure out the sum of squared errors by using our sum of yi minus yi hat squared formula. And we can find the sum of squared errors for this region, for R1, let's call it. And we can find the sum of squares for R2. And when we add those together, that's going to give us our total error sum of squares for the split when x equals w. So that's one error sum squares. We do that for all possible partitions, all possible splits, and we figure out which one is the minimum, and we use that split. And then we iteratively go through this entire process until we meet some stopping criteria. And there's four different stopping criteria. One is if you reach a minimum number of observations to create a split. So that's one stopping criteria. Another stopping criteria is you meet the minimum number of observations. So in a split, I mean minimum number of observation in each region. There has to be some number of items in each region in order for you to actually even perform that split. So if you get to a point where you're not able to do that, that node cannot be split. And then the second is the minimum number of observations in the terminal nodes. In the terminal nodes. So after we have made the split, we want to have some minimum number of observations in each of these different regions. Third is the max depth. So if the max depth is okay, we can't split more this node more than like two times, then that's our stopping point as well. And the fourth is the CP, or the complexity parameter that we'll go get more into. And this is essentially we have to attain some minimum reduction in SSE when we're making a split. So this is what we call the complexity error parameter. You can think of this parameter as sort of a regularization parameter. As in linear regression, we know that when we apply regularization, we're increasing the bias so that we're able to generalize well to new unseen data points. And so here we're doing the same thing. Here we're making sure that we are increasing the bias. So our model, our decision tree is not overfitting to the training data and training data set, and it could generalize to new unseen data points. So that's complexity parameter. And as I mentioned, you can think of this as the regularization parameter. You can think of this as sort of the bias variance trade-off parameter where you're trying to increase the bias, you're trying to make the model more general, and it's really not going to overfit the training data set. So that's what we're doing here. And there's four different ways to make sure that we're doing that, four different stopping criteria. So that's that complexity parameter. So let's just go over what the complexity parameter is. It's something between 0 and 1. If we have 0, that means there's no complexity parameter. That represents the full entire tree. That's the full tree that you can make. And 1 means that we only have the root node. There are 0 splits. So 0 and 1 are the both sides of the extreme. 1 is it's too general. 0 is it's overfitting to the it's like almost exact it's way overfitting the training data set. So we want to have some sort of balance between bias and variance, and we're able to do that through adjusting this complexity parameter between 0 and 1. Okay, and so how did this work? So we know that it's SS, the formula for this is SSE 0, SSE, I think it's 0. Actually, let's not go through the formula. Actually, I can check. So the formula. So the formula in terms of the complexity parameter that we want to apply is the error sum of squares for the current tree plus CP times the number of splits times the error sum of squares of the tree with zero splits or only one node. And so here, so for example, a question could be, when would we favor a zero split tree over a one split tree? And you can plug in the values over here, and you can see for what CP values would it favor a zero split tree over a one split tree, or for what values would it favor a one split tree over a zero split tree. And typically in practice, we want to, after we've built our decision tree, we want to use complexity tuning after we built it instead of reconstructing the tree itself. So let's say we build this decision tree, and so let's say this is the tree. Now we apply our complexity parameter. Let's say our complexity parameter is like zero point 0.4. Then we evaluate each of these splits. So let's say this is split 1, right? We've split this is split 1. This is split 2. This is split 3, split 4, and split 5, right? And now we're seeing, okay, do we want to keep the split 5 or split 4? We perform our calculations and we want to minimize that. So if whichever one is greater, then we're able to get rid of those splits. And we keep on going until we reach the point where the tree that we want to split is actually not greater than the tree that we don't want. So the equation doesn't satisfy. So if at any point we get to a place where SSET plus CP times the absolute value of T, SSE 0, right? So this is, if that is ever less right? So if it favors that split, so for example, let's say this is five splits, right? One, two, three, four, five. Let's say this is five splits. And we see that the four splits doesn't actually make this value any smaller, then we know that this complexity parameter favors five splits. And so we're done. We don't need to prune anything. But if the four split actually results in a smaller value for this equation here, then we can get rid of that fifth split. So we're able to continue doing this until we get to a stopping point where we favor the entire tree that we are left with. And typically, what complexity parameter is determined through cross validation. So when we do cross validation, we figure out what's the minimum error, and we were able to use that as our complexity parameter. And then I'm just going to go over NFL trends here real quick. So NFL Week 6, I have official pick as Bengals money line. I think they're -3.5 or something. I guess yeah. Official pick is Bengals money line. They're favored by I think -3.5, and the reason being is that the previous week, last week, Sunday Night Football upset, and it's very rare to have consecutive Sunday Night Football upsets. Other trends that happened today as well that went aligned with the trends that I've been seeing is Lions beat the Cowboys. Lions were the favorite, and Cowboys have already done a 325 upset, so it's very rare for teams to do multiple 325 upsets in this even in the same season, and they were coming off of an upset as well. They were coming off of upsetting someone else in prime time. So that's why the Lions they won today, and that was aligned with my trends. And then the Raiders, same thing with the Raiders. The Steelers won, and the Raiders had also upset someone else. I think they upset the Browns or something. A 325 305 slot. So that's why the Steelers won, and that falls in line with the trends. And I think yeah, those are the main two lines in the Steelers. And then also like another trend was is this Bengals money line that I have today. So that's the official pick, Bengals money line, and then the two other picks, the Cowboys winning and or the Lions winning as well as the Steelers winning. Those follow the 325 upset trend. Like in a given year, if a team upsets another team at 325, they're probably not going to upset another team at 325 that same season. And so that trend has continued today. And official pick is Bengals money line for tonight. All right. I think that's about it. Thank you very much. I'll see you in the next video.